And today, as I said, he's going to be speaking about gender in physics. Off you go.
Thank you very much, Ernie, and thanks to all of you for coming today. I think I know most of the people in the crowd. A few new faces, which is nice. So today I want to talk to you about gender in physics and cover three bases, so to speak. I want to share with you what the education research has told us about this issue. I'd like to share with you my own research from the data that I've collected with my classes, and also share with you my own experience as a guy, realizing that there's this whole other universe of experience of physics. And so, to begin, I'd like to help us understand this problem of finding a good gender balance in our physics programs. In my school, in our grade 11 physics program, we have 40% females. Come grade 12, it's down to 31%. And I asked Jason Harlow at U of T, how are things going there in your first year physics program? And for physics majors, it's 25%. So, if he wants to make an improvement there, then, we have to do something here. So we need to figure out what is the nature of this challenge? What are the factors that are influencing young women's choices in education? And so there's obviously something going on before grade 11 physics, because we're not getting the balance at that point. And then it's continuing. It's increasing as time goes by. So our goals today, to make a stab at understanding what is taking place, and to look at some possible solutions. So, we want to go from some possible explanations to interventions. What can we do in our classrooms and in our programs to help change this? So the first idea that I'd like to talk about is the idea called self-efficacy. So this is a personal characteristic that we all have. It's a sense in our personalities that we can accomplish something. When we're given a task, we can do this. We have the skills, the abilities to get something done. Good old Rosie over there. So it is widely believed in the educational research community, even outside of physics, that this is a very important personal characteristic which strongly correlates with success in a wide range of educational fields. Now, if you're interested in the particular pieces of research that I draw this information from, I've cited the sources here. I'll just give them the title. You plug that into Google Scholar, it'll bring up the original article. And this presentation is also available from my website, so you can just download the PowerPoint if you prefer to do that rather than scribbling down all the little details. So you can track down the research that I'll be citing here. So self-efficacy, what can we learn about our physics students and their self-efficacy? Well, if we ask them simple questions about how they feel in their physics classes, what they can accomplish, and we give them a rating of average self-efficacy, we can see the scores for females, so these light shaded bars, and the scores for males, the darker bars. And there's a clear difference in these distributions. So females regularly rate themselves lower in terms of their own perception of, yes, I can get things done, I can figure out my problems, I can work through this lab. So there's a very clear difference in male and female responses, at least to this question survey. And it also brings up another very interesting aspect of monitoring and trying to smooth the gender differences in our classroom, because the researchers noticed that they seem to be discovering something called a male overconfidence syndrome. I'm not sure if you've come across this in your own teaching experiences. I certainly have. And the surprising thing they found was that male students going into first year physics with no prior physics background are the most confident in their own abilities. So the people who know the least feel, oh yeah, we've got this under control. And when they track this longitudinally, they notice that, again, for this group of males, a distinct lack of correlation between their marks in the course and their self-efficacy scores. Whereas for the women, they tracked relatively closely. So there's a very interesting psychological dynamic going on with a portion of our male population. And I think this is very important to recognize and understand when we are monitoring how our groups are working in our physics classes. Because this has a genuine effect on our female physics students. I've seen it enough times in my own class that I'm very careful to prevent these situations from arising. We'll have a group of 2 boys and one girl, and they're working on their physics activity for the day. And the girl is sending out all the right ideas. She's got the answers. And the boys are just talking right past her to one another. And it's like she's not even there. They know the answers. They know they're on the right track. So I try to avoid setting up that situation. I'm very careful in how I construct the groups that my students work in. So a very important aspect of the self-efficacy issue. Another important aspect to consider is the use of equipment in our classrooms. A study was done by UBC just a short while ago, looking at male-female pairs in their classroom and the fraction of time that the females used equipment. And we can see here that there were 9 pairs where the females basically did not use the equipment. And again, this is something that I've observed in my own classroom. Now, they also remarked that the sample size is fairly small, so the stats aren't strong here, but it backed up my own experiences. And so this is another issue that we need to be conscious of as educators. And then there's the issue of gendered questions. So perhaps the phrasing, the construction of the questions and the tasks that we give to our students has an effect on their ability to figure them out and their ability to unpack these problems. If you delve into the older physics textbooks, you'll notice a lot of male-oriented type of questions. They often involve situations that would be sort of stereotypically male, or they might be situations that are very abstract, decontextualized. And so perhaps this is a factor in how our female students perform in our class. So they did a very interesting study here. They took some questions from the well-known force concept inventory, and I'll talk more about this a little bit later. And here's a classic abstract question. This question has no real physical context. It's just blocks moving along. And I know in the past I've written a lot of physics questions on tests that were just about blocks. And they changed it. They said, okay, we're going to give them the exact same question, but we're going to put it into a context that is a little more familiar. So instead of having blocks, we now have joggers. Anne and Pam are jogging along. These are their positions at the different intervals of time. So how does that change students' responses to this question? It's testing the exact same physics. If we look at the original response rates to this question, 42% of the males answered the block question correctly versus 32% of the females. So what difference did the context make? It made a very big difference, but also a surprising difference. It helped out all of them, but that difference between the male and female response rates was still there. So clearly, having contexts for our problems is a very helpful thing for our students. This is one important takeaway from it. But there's obviously something else going on here. And as part of this study, they also had some questions that were phrased in using stereotypically female situations. And they found similar patterns as well. So changing the language didn't reduce the gap helped all of them, the gap is the same.
The absolute gap is the same, but the relative gap is reduced.
Yes. Yeah. So another idea that researchers have explored is that of physics identity. So this is your sense of belonging to a particular community. Our community is of physicists. You feel like you could be a physicist. When you enter the classroom, you feel like this is a place for you. And we've already been hearing stories from people at our conference of, when you're that female entering the 80% of males classroom, that has a real effect on you. And I have to admit, as a guy, that I was really kind of clueless to this for a long time. It really wasn't until my daughter was about 2 years old that I realized how early on people start to see the world in a gendered way. Because from that young age, she was already making very careful observations about the things that women do and the things that men do. And she really wanted to do the women things. And that was really an eye-opening moment for me of just how deep this might be a part of our psychological makeup. And just as important, how conscious we should be as educators of the power of this effect. So, at the University of Colorado, they gave a survey where they asked students some questions about their physics identity. And the numbers tell a very interesting story. So I enjoyed physics this semester, 42% of the males, 19% of the females. I feel like I could be a good physicist, 54 to 20. That's a huge difference. That's a really big difference. And again, there's obviously a different universe of experience happening here than anything that I was familiar with. And they had some questions about the self-efficacy that I previously mentioned. And so here you can see some of the results. Again, very clear differences between the male and female responses to these questions.
You know whether it's male or female?
I'm sorry?
Who was the instructor, male or female?
That I don't recall. Yeah. Yes, sir.
But the male, I felt like I didn't belong.
Yeah.
67 male, 39 female.
Yeah, this is an interesting
and then the
result.
physics makes me feel uneasy. 53 for the male, 21 for the female.
Mm-hmm.
And then I got really stressed, 30 for the male and 10 for the female. So like some of those questions, it seems like females were less uncomfortable.
There's quite a variety in the flip sides of the responses here. And the important thing to take away is that psychologically, our male students seem to be experiencing our physics courses differently from our female students. And it's important for us to try to understand what are these differences and what sorts of things can we do to try to help all of these improve. Yes, ma'am.
Well, from my experience, I would think maybe it's because, like with so many males in the class, there's a sense of competition between them. So they're trying to, be whatever, like the best guy in the class. Whereas the girls aren't necessarily pulled into that. Like I didn't feel like, I feel like I'm just competing with the other girls in the class, like when I was that age. So maybe the stress isn't there to perform at that level.
There's probably a very wide variety of factors, and the levels of complexity, all the different levels of nuance, is no doubt very great. So this idea of physics identity, just generally speaking, females report a distinctly less sense of physics identity. This is a community that I could belong to or feel comfortable in. And the researchers believe that this one factor could be a major one in explaining the difference in their performance in the courses and in their enrollment in them. There's the study there if you want to follow up on the details. Now, another part of this, related to physics identity is the stereotype threat. So this is a psychological idea that was well studied outside of physics before we started looking at it. And it's the idea that you're afraid of doing something that would trigger that negative stereotype. You know, you're afraid of answering that question and getting it wrong, because then people will think, oh, well, it's just one of those people. And this seems to have a very powerful effect on people. And according to the research, they're thinking this could be a strong contributing factor to the differences in performances. Now, another way of exploring the differences between our male and female students' performances in our physics classes by trying to measure their understanding and looking at their performance on conceptual surveys. So, the researchers wondered, can we measure how much are girls learning in our classes versus how much are the boys learning? And one of the common tools for doing that is the force concept inventory. Now this, just in case you're not familiar, is a very widely used conceptual survey, 30 multiple choice questions, no math, about your basic motion and force concepts. It's being used around the world, so it's a very valuable tool for comparing your results with others and comparing your students' understanding at the beginning of your class, beginning of your course, and at the end. And that provides you with a measurement of how much they learned. It's been used for a long time, very, very well researched and scrutinized survey. And if you aren't using this in your classrooms, you really ought to be. So you get some basic measurements. And as scientists, we know it's all about the measurements. So if you're not measuring your students' understanding in some way, then you're missing some very valuable information for your own learning about teaching. And here's some results. So this was a very large meta-study that was published showing the scores on the force concept inventory. So the test is usually given at the beginning of the course. And at that time, the scores broken down by gender. So the green is female, the blue is male. And we have a variety of universities here. This is Eric Mazur at Harvard, just for those who are curious and are familiar with. And we can see, and I've added in my own scores from our grade 12 program at York Mills in Toronto. And that very consistent starting gap in knowledge. Now, in truth, this is not really the starting point, because their understanding of forces and motion began well before they enter our first year physics programs or our grade 12 high school course. But at least when we make this snapshot, we already see a clear difference. And it's very consistent. So pretty much across the boards, there's a gap of about 10% between the pre-instruction scores on the force concept inventory. Now, the researchers often give them the exact same test at the end of the course, and we look at what's happened to the scores. And if we look for patterns, we can see in the majority of cases that gap is still present. So by the end of instruction, the boys are demonstrating more understanding on the survey than the girls, the women. There's a few cases where it's narrowed, but these seem to be the exceptions. So again, that gap remains about 10% on the post-test. So one final measurement that is commonly made using this tool is, well, how much improvement did the students make? How much did they gain in this conceptual survey? Because that's a measurement of how much they learned from my class, from that course of instruction. This is kind of the gold standard for judging how much students are getting out of your course. And the gain has a gap of about 6%. And we can see it's fairly consistent. There's a few that are, so again, Eric Mazur at Harvard. Here, its sample size is very small. And in my own school, a clear difference in the gain. So during their time in that course, the boys are learning more or developing more understanding than the girls. And this is what the data is suggesting. Now, what's really interesting as you dive into the analysis is there's certain questions on the forced concept inventory that are like landmines for the female students. Questions 14 and 23. I wonder how my female students do with this. And it was spine-tinglingly unnerving how closely my data tracked the widely reported research results. Question 14, there's almost 20% difference in how the male and female students perform. Question 23, even greater difference. And what's going on here? We need some PhD students to do an analysis of these questions and the gendered responses to them. Because to us, they seem like stock physics questions. The classic question of dropping the object from the plane. It's going to follow that projectile path. The rocket's traveling along like this, turns on its thruster, which exerts a force pushing it upwards for a short while, turns off the thruster. How does it move afterwards? No forces, it's got to move in a straight line. So both of these questions seem to present special challenges for our female students, and I'm convinced there's something really important that we could learn from studying this. We should be interviewing our female students and studying their thinking process as they answer questions like these. So, have your PhD students, there you go. So the researchers have wondered, we have this very consistent and clear pattern in the survey results. So what can explain this difference? So they've collected vast amounts of data that explore different background factors. And so they're doing their regression. The statisticians love to do these things, find all the correlating factors. And they found a lot of factors do not explain. And whether or not you had high school physics, so on and so on and so on. These don't seem to explain this very noticeable and consistent difference in scores. Now they continued their analysis, and they found a factor which might explain it. SAT math scores. So perhaps the mathematical preparation of the female students is a factor. But even with the vast quantities of data that they have, the stats weren't strong on this. So this is more of the open question. And so their conclusion was that this gender gap is probably a very complex combination of many of these factors that we've explored today. So the problem that we're facing, the challenge, is very complex and nuanced. But maybe there's something to this math angle. And thanks to Roberta for sending this article my way. So it just came out about a month and change ago, looking at the sex differences in math anxiety amongst students on the International PISA math survey. And what they noticed is, in countries where gender equity is very imbalanced, so where there's very great gender differences in society, math anxiety levels between males and females are very similar. But when you move to countries that tend to perform well on the survey, that they also tend to have much greater gender equity within those societies, a gap widens between male and female anxiety levels towards mathematics. So especially in Western countries, we see quite a wide difference in that anxiety or confidence level of our male and female students. This was a very surprising result that came out of this survey. Yeah, I encourage you to track it down and read it because it's a very interesting one. So maybe there is something to this math anxiety factor. So that, I suppose we'll have to wait for future research to help us draw a firm conclusion. But that anxiety is there. And there is a real difference between how our male and female students experience it. So at this point, that's something that we need to be very conscious of. So we've explored a lot of possible factors that are involved in these differences. So what can we do about it? Well, the researchers have been trying a lot of different strategies. So let's take a look at what they've been up to. So the great hope was interactive engagement. So this is the major shift that's been taking place over the last couple of decades as we transition from traditional lecture-based instruction to instruction that actively engages students in the learning process through peer instruction, the questions with clickers in class, or cooperative group learning. There's a variety of forms that this takes. And what researchers believed is that this mode of instruction was, or it might be, more conducive to those stereotypical female characteristics of cooperative work and discussion-based learning. They thought, this might be a good match. And they found some interesting results. So if you look at interactive engagement, so these different institutions are listed according to their mode of teaching, so interactive engagement. Modeling instruction is another type of interactive engagement, versus they got the red box for traditional instruction there. Well, we can see that from lecture-based learning, students learn relatively little. 20 to 30% improvements on the force concept inventory. Whereas with interactive engagement, the results are much greater. So the data is very positive in supporting the success of these strategies overall. But those gaps, those gender gaps, are still largely there. There's a few places where it seems to be reducing or disappearing, but the factors involved there are not clear. So it might be, again, a very complex interaction of a variety of things. But even with this very different way of learning, it helped out our boys a lot, and it helped out our girls a lot. The gap is still there. So it's a very fascinating piece of this educational puzzle. So both increase, but the gap is there. So another strategy that's been tried out, this is the University of Colorado, was a self-affirmation intervention. So again, outside of the physics community, it was known from psychological research that if you bring